Okay, we started recording. Hello to everyone. Let me share the screen. Okay. Um, so we are continuing from last time about the stream cipher construction and what is a pseudorandom generator. Um, so okay. So just a brief recap, right? So the idea is to, instead of taking a key for a one-time pad, we expand the key using a PRG, a pseudorandom generator, the output, and we use the output of the PRG on a key as a one-time pad. Otherwise, it's the same as one-time pad, and we need this PRG to be deterministic. And what are the properties that we need? So we want outputs of a PRG to be indistinguishable from random strings. And just to cut to the chase, we talked about like different ways that you can think of distinguishing random strings from strings that came from some other distributions. Such distinguishers are called statistical tests. And we define PRG to be secure, or in other words, an algorithm G, which is a function from some key space to a larger space, to be a PRG if it's deterministic, and for any efficient adversaries, which are basically statistical tests. If you define the advantage of the statistical test attacker against the PRG as the difference between the probability that the attacker outputs a fixed flag 1 when he gets an input which is an output of a PRG on a random key, on a random seed taken from the domain of the PRG. And you compare it to the probability that the same test outputs the same flag, but when it's given an actually random string. If the difference between them is negligible, then PRG is secure. And if it's negligible for every statistical test, right? So intuitively, if these two probabilities are far, how can that be? It must be a statistical test that acts, like for example, on a random string, it's almost never outputs 1. But on an output of G, it outputs 1 always, let's say. Well, so in this case, the probability here is 1, and the probability here is something very small. In particular, you cannot prevent, it cannot be fixed to 1 because you cannot prevent a random string to somehow magically look like GK for some K, right? It's not by magic, it's by some probability. Outputs of G will reside in this space. So outputs of G resides in this space. So a random sample from n-bit numbers with some probability falls into pink region, in which case that random sample is indeed indistinguishable from a random output of G on some input, right? So this distance cannot be fully 1, but it can be very close. Conversely, if it's close to 0, that means that A on outputs of G, random outputs of a PRG, acts basically the same way as on random strings. Therefore, A fails as a statistical test that distinguishes output of G from random strings. And if that is the case for all efficient statistical tests, then we are happy with the PRG. The G is a PRG. Here is an example I skipped last time. So let's say that G has this property that if you look at outputs of G, then the most significant bit of these outputs is 0. So the first bit or the last bit, whatever you count, most significant bit, is 0 for 2/3 of the inputs. So you sample a random seed and you run G on it, and with probably 2/3, the output of G will have the most significant bit 0. So here we go with a statistical test. He gets a sample, and the goal of the statistical test is to distinguish between outputs of G and random strings. So let's test for this condition. And if it is the case, then output 0, otherwise output 1. Let's look, what is the advantage? So what's the advantage of this statistical test? Okay, let's compare probability with which this test outputs 1 when it gets outputs of G, to the probability that this test outputs 1 when it gets a fully random number. And now, when is A outputs 1? It outputs 1 if the MSB of the input is not 0. But by this property, MSB of a random output of G is 0 with probability 2/3. So therefore it's 1 with a probability 1/3. So this probability is 1/3. Let's compare it to here. Well, this is a half, right? Because R is a random string. On a random string, the probability of its MSB is a random bit. So this is gonna be 1/2 probability, and this is gonna be 1/2. Okay, so this difference is a constant, and it's not negligible, right? Because a constant is a not negligible amount. Okay. If the outputs of, so this basically you can generalize this. If outputs of G have any properties that can be efficiently tested, such that the same properties are, do not happen with the same probability on random strings, right? So there is some information function you can compute on outputs, which if it is an output, then with high probability it will satisfy it. But a random string satisfies probability 1/2. Then that will be an attack against the PRG. And any algorithm G that whose outputs can be tested in such a way will be an insecure proposal. So this is where we ended last time. That definition of PRG is that this difference is negligible. And it is the same as to say the following. The distribution of outputs of G on random seeds is indistinguishable computationally from the uniform distribution of a random n-bit strings. Because that's what this whole thing says, that for all efficient algorithms, if you define an advantage of the algorithm as precisely the difference with which he acts on a random sample from the left-hand side and a random sample from the right-hand side, then the existence of such an attacker would violate this notion, because this indistinguishability here says the same thing as above, which is that for all efficient attackers, probability, if you measure probability that the attack outputs 1 on samples on the left and subtract from it probability that he outputs 1 on a random sample from the right, they are negligibly close. Okay, let's recap. Is there some questions to this slide so far? Or to anything I said so far, like a recap of last time? I will just put it on one slide then. So we have this notion of what it means for two random variables or two distributions to be indistinguishable computationally, right? The notion is, again, for all efficient attackers, if you measure the probability that the attacker outputs some fixed flag, let's say 1, on a random sample from this distribution, and you subtract a probability that the same attacker outputs the same flag on a random sample from this distribution, then this difference must be negligible. It's bounded by a negligible, from above by a negligible function. Now, having this notion of indistinguishability between two distributions, we define two things. One is this computational notion of security for encryption, which we called indistinguishability of encryption, and also semantic security for encryption. And the notion is, I call an encryption indistinguishable, semantic secure, computationally secure, if for all messages M0 and M1 in message space, if you look at two distributions, the left one is a random encryption of M0, the right hand is a random encryption of M1, where randomness goes over random choice of key in both cases and randomness of encryption if it is randomized. And you feed this sample from this or sample from this to any efficient test, then this test is basically going to act almost identically on these two, where the almost is that if you subtract the difference, it's negligible, right? So likewise, this notion of indistinguishability of distributions also allowed me to define what a PRG is. So pseudo-random generator is a deterministic algorithm which is efficient, polynomial time, which takes a seed of fixed length, expands it to regardless of what the seed is, as long as if it has alpha bits, lambda bits, I think on the previous slide, then the output will have n bits, which is some function of lambda. Let's say twice, or square, or any polynomial. So it's a deterministic algorithm with the property that if you look at the distribution of outputs of this PRG, where the distribution goes over random seed. So you give him a seed, he gives you this expansion. You give him another seed, he gives. So the process is, he takes a random seed and expands it and gives you the PRG string. Then these outputs to every efficient algorithm are indistinguishable from random strings. That's why it's called pseudo-random generator. It creates these long strings. He had to have some initial randomness. You cannot deterministically create a string because everybody would recognize it. How? Just rerun the same deterministic algorithm and check, right? Again, no security from obscurity. So PRG code is known. So everybody could run it, right, in a forward direction. So how can you, the only hope is that the space of seeds is large enough that it cannot be brute force searched. So the inherent security of a PRG is 2 to the lambda, where lambda is the number of seeds. Because in fact, you could be searching through all the seeds and run the G forward and then simply test for equality. But that's exponential time attack if lambda is a security parameter. So this G takes this lambda bits of entropy and expands them. How? Deterministically. So it's not a random string with more entropy. There's only lambda entropy. And if n is much larger, then there must be tons of correlations between these n bits. And yet no efficient algorithm can tell what the correlations are. Okay? So to everybody, it looks random. This is an incredibly fundamental concept in cryptography, because if, you know, that's one of the first things that is wrong in systems, that randomness is not really good quality, that whatever nonsense some algorithm, TCP, window offsets, you know, all sort of nonsense which are supposed to be random, if they could be predicted then a lot of security guarantees in systems just go away. So this says, okay, if you had some truly random entropy at the beginning, then you can hook it up, and from that point on, you don't use some pseudo entropy, generator. No, you use you just expand this initial entropy you had using pseudo random generator, and well, if security of a PRG is believed to hold, then the output is as good as truly random bits. We will use this all the time in crypto, this thing. And the first thing that you'll see where it works is that the following construction of encryption works. That if I encrypt by using a short key, think of lambda as 80 bits, expanding it using a PRG to some polynomial amount, however much the message, however long the message is. And I use the same quantum pad now, but won't expand it. Then it satisfies this notion. So random encryptions of whatever message are indistinguishable from random encryptions of another message. And if you believe that this relaxation of perfect security to this indistinguishable notion is fine, if you are okay with it, then you will be okay with this construction. So let's see how this works. And this is the stream cipher. So this okay, I think this slide actually repeats what I just said, but like in a maybe nicer way, right? So this is the construction we want to check. We start with an assumption that G is a secure PRG. In other words, that these kind of that PRG outputs are computationally distinct from random strings. And what our goal is to prove that this encryption has this property. So no matter what M0, M1 are, if I compare distribution of random encryption of M0 with distribution of M1, they will be indistinguishable. And here is the unwrapping of the indistinguishability notion. It's again the same notion. So, well, we are in luck because we are showing this. I'm not in luck because here I have E and here I have enc, but that's a typo. This enc and this E is supposed to be the same thing. Okay. So minus that spelling typo, right? I will replace the encryption, this abstract encryption, with this particular case, right? So what I have here is really G of k XOR M0, and what I have here is G of k XOR M1. So that's what I want to show, that G of k XOR M0 and G of k XOR M1 are indistinguishable. So here is the intuition of the proof. Attacker on the encryption has to fix these messages. So in order to violate this, I have to find some M0, M1 and distinguish this distribution from that one, right? Then I violate this. So I want to argue that this cannot exist. Okay. Or the only way, actually I cannot prove this without conditions. I will prove that this attack cannot exist if there is no attack against this, right? So if this is true statement. Okay, so here is this attacker which chooses M0 and M1, and then it either gets a sample which is a random encryption of M0, but it's a stream cipher, so random encryption of M0 looks like M0 XOR G of k for a random seed k, or he gets a random encryption of M1, which means he gets a random sample that looks like M1 XORed with G of a random seed again. I want to show that these two are indistinguishable. Okay, so first is that I will replace this view with a similar one, where instead of the real encryption, I have a modified encryption, if you will. The modification is that rather than use stream cipher and pick a random stream cipher key and run the stream cipher by running the PRG on the key, instead I pick a random string of the same size as M0. This, by the way, is a one-time pad. And intuitively, there should be no attacker that distinguishes this type of this sample from this sample. Why should that be the case? That no efficient attacker A can distinguish this sample from this, because the only place they differ is on this part. Here, this sample is M0 XORed GK. This sample is M0 XORed R for a random R. So we somehow intuitively, the only thing that differentiates them is that here GK was used and here a random string was used. But under the assumption that no one can tell efficiently outputs of GK, these values from these values, so hopefully it also is the case that no one can tell GK with post-processed by XORing with M0 from R post-processed in the same way. We will see that this actually is a very formal argument. It's called a reduction, and it's a very simple case of reduction, but it's still a reduction, which will basically perform this post-processing to show that if this attacker existed, who would tell this from this wire from this wire, then you would immediately construct an attacker which differentiates GKs from Rs, whereby GKs, I mean a sample of a distribution that is formed by sampling a random seed and running G on it. And by Rs, I mean this distribution of uniform n-bit strings. So we'll do this in a second, but this is the intuition that because G is a PRG, XORing its output with the fixed constant and XORing random with the same constant must be indistinguishable still. Now, by the one-time pad argument that we've already done, we know that this idealized encryption scheme, the modified encryption scheme, is a one-time pad, so it's perfectly secure. So we've already seen that this distribution and this distribution is the same, right? That was the one-time pad argument. And of course, this final one, it goes by the same logic as this one. I didn't assume anything about M0 when I was intuitively, hand-wavingly arguing that XORing GK with the string and XORing R with the string must produce indistinguishable distributions if GKs and Rs are indistinguishable. So the same argument goes for XORing GKs and Rs with M1. Yes, there was nothing special about M0 here. And finally, because computational indistinguishability is transitive, so here you have some distribution, okay, call it G0. Here you have some distribution, call it D1. Here you have some distribution, call it D0 prime. It's a modified distribution of encryptions of M0 by basically changing the encryption scheme, in this case, replacing stream cipher with a one-time pad. And let's call it G1 prime. So I have 4 distributions, right? G0, G0 prime, G1 prime, G1. And the first 2 are indistinguishable, then the second and the third are indistinguishable, and the third and fourth are. Indistinguishability is transitive, and it's not hard to see that it's transitive because, look, these are 2 distributions, right? What does it mean that they are indistinguishable? It means that if I take a test, I feed him with samples from this, and I feed him with samples from that, he behaves negligibly close. So now I have the same statement about P2 and P3. That if I give him P2 samples and P3 samples, he still behaves negligibly close. So how big of a distance could there be between the way he behaves on P1 and the way he behaves on P3? Where's just sum of these those 2 epsilon bounds is epsilon that measures the difference between P1 behavior on P1 and behavior on P2, and epsilon that measures the difference between behavior on P2 and P3, and so forth. But each of these epsilons is negligible. So a homework will have a simple exercise that if you add a bunch of negligible functions, you get a negligible function. It's really just an obverse of the known things, like that if you add a bunch of polynomials, you get a polynomial. It's just that because we work with like 1 over polynomials, so it's a little harder to see, but not much harder to see. Likewise, multiplying a negligible amount by any polynomial amount. So here, in this case, we had a sequence of distributions that was 4 of them. We could actually have polynomially many. And we would encounter, if we encounter negligible amounts at that step, this is still negligible because negligible amounts multiplied by a polynomial still give a negligible amount. So that's also an exercise to just go through to understand this negligibility notion. It's like once you see it, it's obvious, but it's good to work through it. Okay, so that was the intuition for why, it is a generalization of a one-time cipher and of a one-time pad. And in a sense, what the requirements of what a PRG is exactly what is needed for this construction.
Professor,
so
can I ask a question? Okay, so polynomially many negligible functions, right? Mm-hmm. If they are different, I can see that would be true if they are equal, but not necessarily if they are distinct, because the point at where you will be less than a certain polynomial, certain reciprocal, mm-hmm. may change for each one.
Yes. So that's why it's yes. It's not as simple as like if I multiply, if I take polynomially many polynomials, mm-hmm. that's the sum is always a polynomial. All right.
Right.
Yes, you have these issues with the thresholds and so forth, but like, so that's why it's good to think through. It's not that hard.
Yeah, so, if they are bound by one negligible function, then I can see it working.
Yeah. Well, okay. So you can, you don't see this right this second, but you will when you look at the piece of paper and think a little bit.
Okay. Thank you.
Yeah. So it is not perfectly trivial by this exact reason that, that basically the notion of indistinguishability, right, is that, the notion of negligible functions is a sequence of quantifiers for all polynomials. There exists a point such that after that point and so forth. But just think of like 2 of such, and you will see that you can set these. So your thresholds will be functions of the other thresholds, and your polynomials will be functions of these other polynomials. And but they're like sort of natural, there's it's not very complicated, but you have to look at it. So that was an intuition. Here it is more formally. Formally, we are arguing that if a G is a secure PRG, then stream cipher using this G is indistinguishable encryption. And basically, we will prove this by counterpositive. So what we are trying to show is of the form G implies E. Security of a PRG implies security of an encryption. But this is a common thing in proofs that actually it's sort of more convenient to think of this way. Think of it the counterpositive, which says if encryption is not secure, then the PRG must not be secure. And the reason that it's easier to think of counterpositive is that because security of a PRG means that for every polynomial attacker, something happens. Security of an encryption, again, is that for every polynomial attacker, something good happens. I mean, that he has low advantage. So counterpositives have a nicer form, really, because negating that encryption is secure means that there exists an attacker on encryption. And negating this part means that there exists an attacker on a PRG. And that's an easier direction, because basically what we'll do is say, okay, fine, let's take this hypothesis that there exists an attacker on encryption. Let's call him A. We will show an explicit construction of an attack against a PRG, and we'll call this attack B. B will be built using A in very, very simple ways. In this case, this building of an attack against PRG, if somebody gives you a box that attacks encryption, that's called a reduction. Okay, and so so what we will show, to be precise, is that if you give me an attacker, an adversary A, and it attacks the encryption, so it has some non-negligible, in other words, 1 over polynomial advantage in encryption security game, then I will show you an attack against a PRG such that the advantage of this attack on against the PRG is some polynomial function of this advantage. So if this was 1 over polynomial, then so will this be. Here it's a very simple. Actually, the attacker on a PRG has almost the same advantage as the attack on the encryption, just half of it. Okay, and in the cryptographic terms, like constants don't really matter. Okay, so that's the angle of the proof. Again, we'll assume that there is an attack on encryption, and we'll show that that can only happen if there was an attack on PRG. In other words, we'll construct an attacker on PRG from this supposed attacker on encryption. Okay. So let's start with an attack on encryption. Now we know what form it takes. It is, we know the notion. We know that we are attacking indistinguishability of encryption. So we know what that means. If you attack indistinguishability of encryption, you must be producing some 2 messages such that if you get a random sample of the encryption, and by the way, we're proving security of stream cipher. So we know that this encryption is this one. So it's an encryption under key K of M is M XORed with PRG applied to K. So there is a secret bit here that defines a security game. And what the attacker sees is MB, so either M0 or M1, depending on bit B, XORed with GK. An attacker must output B prime. And by assumption, his probability that B prime is 1 if B is 0, and the probability that B prime is 1 if B is 1 is different. So let's denote these two experiments. I will index with bit B two random variables. WB will be an event that adversary output 1, in other words, B prime is 1, when adversary interacts with this box indexed with B, okay? So he gets an encryption of MB. So using this terminology, an advantage of this attacker against indistinguishability notion is the difference between the probability of W0, which is again event that attacker outputs 1 given M0 XOR GK here, and probability of event 1, which is attacker outputs 1 given an encryption of M1, so given M1 XOR GK. And by assumption, we are supposed to start with that. Let's say that this attacker exists, and we'll show attack on a PRG and end the proof. So this corresponds to we are basically measuring. We are calling this event W0 and this W1. So this will be the probability. How he acts here will be the probability of W0. This will be the probability of W1. I will now introduce variables that correspond to these intermediary modified games. So I will call them R of B, the random game, where instead of so here I had the adversary gets MB XOR GK, and here I now will give him MB XOR R for a completely random R, right? And in the case where GK is replaced by R, I will call that an RB. So again, RB is the event that adversary output 1 given MB XOR R. Okay. So let's make some. Okay. So here is these two in the recapped. WB is the event that adversary outputs a flag on a real encryption of MB. And RB is the event that he outputs the same flag on a one-time pad encryption of the same MB. So claim probability, the difference between probability of R0 and R1, who can say? What is the difference between the probability the attacker outputs 1 given M0 XOR R with the probability that he outputs 1 given M1 XOR R, where R is perfectly random string? Okay, 0. Yes, good, good, good. I have a bunch of zeros. Thank you. Precisely. Yeah, it's a 0 because it's an advantage in the semantic security game of the attacker against a one-time pad. This encryption is a one-time pad and it's unbeatable. No matter what this attacker does, the advantage is 0 because these two values, these two random samples are the same. They are just uniform n-bit strings in both case b equals 0 and case b equal 1. Okay. Now we'll show that if that there exists an attacker B such that capital B, that no matter what the little b is, whether it's 0 or 1, the difference between the probability the attacker outputs a flag on a random sample like this, so a real encryption of MB, and the probability that the attacker outputs this flag on a random sample from this, so a one-time pad encryption of the same MB, that this difference is actually an advantage of this attack against PRG. And again, intuitively, that's because the same MB participated in these equations in the same exact way. We'll do this in a sec. Let's first show that if I knew these two facts, then this follows. Then I'm basically done, because these probabilities are some values between 0 and 1. So let's put on the line, let's say this is probability of W0. This is how he acts on real encryptions of M0. This is how he acts on encryptions of one-time pad encryptions. And it doesn't matter which one because they're identical. This is just how he acts on random n-bit strings. And this is how the attacker acts on random encryptions of M1. What this shows is that these two differences are equal to the advantage of B against a PRG. And therefore this distance is at most twice. This is called triangle inequality. If, let's call this point A, B, and C. What this shows is that the distance between A and B is some fixed distance, and distance between B and C is some fixed distance. The distance between A and C is upper bounded by the sum of the intermediary distances. It might be that it came back, right? That they're not aligned on the line, but in the worst case, you're just adding distances, and it cannot be the distance between the starting point and the end point cannot be any more than all the intermediary distances at every step added. That's called triangle inequality. And we'll use it in security arguments all the time, because we will have this type of arguments all over the time, which is that we'll reduce security of some construction to either attack this, or attack that, or attack this, or attack this. Each of these will give us some steps in this type of arguments, and they will imply that the difference between the endpoints in this chain of modifications of modified games is upper bounded by the sum of all of, in fact, the upper bounds on all the intermediary differences. So the only thing I need is this part, because I'm already done here. Okay, and now I just flipped it. So adversary against encryption is upper bounded by 2. The advantage of A against encryption is upper bounded by twice the advantage of B against the PRG. So let's flip this in this fashion, right? Put 2 as 1/2 on this side. This means that whatever advantage of an encryption attacker was, attacker advantage of B against a PRG is at least half that. So if this was non-negligible, dividing it by 2, it's a constant, the result is still non-negligible. And so it would violate that G was a secure PRG. Whether you see it as a counterpositive or you see it as a direct argument, you can see it either way, right? So, I mean, counterpositive and direct arguments are indeed equivalent. So this actually can be seen as a direct argument as well, that advantage of yes, but anyway, I'm just going to envelop a counterpositive so it's not productive. So the only thing missing is this part. So let's see, finally see how this reduction from distinguishing these distributions to distinguishing PRG distributions that are involved in the PRG game, so GKs from random, how this reduction is done. Okay, so we have a claim that there exists some reduction, that if an attacker distinguishes a random increments of M0 from, okay, it's too bad that I don't have this on this slide, but what he distinguishes is MB XOR GK or MB XOR R. So here I have what he sees is MB XOR GK and here MB XOR R. And let's just take it for B equals 0, so it's easier, but there's nothing special, right? So it's the same argument for B equal 1. Let's build this reduction. Here is the reduction. You are given an attacker which has some distance between how he acts in here, which is how he acts on M0 XOR GK, and how he acts in here, which was how he acts on M0 XOR R for random R. We want to build an attack on a PRG. What's an attack on a PRG syntactically look like? Attack on a PRG gets a string and must decide whether that string is an output of a PRG or it's a random string. That's what it means to attack a PRG. So let's use this supposed attack on encryption, which distinguishes these two worlds, the W0 and R0, to attack Y. And how are we going to do this? Well, okay, look, attacker on encryption, syntactically, he decides what are these two strings, right? That's the first move. And then what he needs to have is an encryption. But actually, what we are assuming at this step is that he sees the difference between a real encryption of M0 and a one-time pad encryption of M0. So these two differ by whether either GK or random is XORed with M0. And B's goal is to distinguish Y as being either GK or random. So what he will stick as a ciphertext to pass to the adversary is this string XORed with M0. Because if Y came from GK, then this string looks like in this world, right? So this looks like it's distributed like M0 XOR GK. But if this string came from a random uniform distribution, let's call it R, then this string looks like M0 XOR R for a uniform R. So it looks like in here. So this reduction correctly correlates the input distributions it's trying to distinguish with exactly the two distributions that A was supposed to distinguish. And this is this simple reduction, right? Take a string, XOR with M0, and that accomplishes it. And so whatever this guy decides, given this ciphertext, just output it. You have no idea how to evaluate it, but the assumption was that this A distinguished strings of the form M0 XOR GK and strings of the form, they were here, M0 XOR R. So look, what is the advantage of this attack? Well, let's measure it. Let's look at it's the difference between probabilities with which this algorithm outputs a fixed flag. In first case, he's given a random string. So this Y is a random string, call it R. In the second case, Y came of a distribution of random samples of G. So random seed, and you run G on it. And let's look, what is the probability that B outputs 1 in these two cases? Okay, let's do case by case. So first is the case where Y is a random R. Well, so when does B output 1 in that case? Well, it outputs 1 if and only if A outputs 1 on a string that looks like M0 XOR Y, which is R. So the probability that A outputs 1 on M0 XOR R for a uniform R is precisely what we call the distinct probability of R0. In this case, how does B act when Y looks like GK for a random K? Well, when does B output 1? Whenever A outputs 1. So the way B will act is the way A will act on strings that look like M0 XOR what? Well, here we have to measure it for Y equal G of K for a random K. So in other words, this probability is exactly the probability that A outputs 1 given M0 XOR GK for a random K. That was precisely this, right? So this thing with M0, yes. So this, ends the proof, right? So this is this reduction that I was promising you, right? The reduction that in this intuitive spot was right here. I said, look, it's gotta be that if some attacker distinguishes M0 XOR GK from M0 XOR R, then it must be that there's the only way to do it is somehow to distinguish GK from R. These last few slides were a formal exhibition that that's the case. That if you have an attacker that tells this wire from this wire, then you would trivially build a reduction that distinguishes GK from R. And how does this reduction work? It takes a string, call it Y. It doesn't know, is it GK or is it R? In other words, does it come from is Y a random sample of a distribution created by taking a random seed and out running a PRG on it? Or is Y created as a random n-bit string? The reduction doesn't know, but what it does with the string is just it XORs M0 in front of it and feeds it to A. And that reduction will replicate this view in case the string came from the GK distribution, and that reduction would replicate this view if the string came from a truly uniform distribution. And that reduction shows that this intuition was correct. Then indeed, the only way to distinguish these two implies distinguishing this part. You have to be careful with these type of arguments because it very much mattered, for example, that the reduction knew what M0 is. It did. Adversary had to explicitly say what a message is. Indeed, it's kind of hard to think of like what does it mean and attacking encryption of, you know, distinguishing encryptions of two messages and you don't even know what these messages are. But we'll see some cases where this breaks. Like for example, what if someone used it to XOR like some other function of the key, which is not public and it's not known. Okay, so that's all that was, and it sort of you know, it corresponds to this step in this intuitive pictorial version of the argument. So this is a good time for questions. Every time it's a good for questions, but okay. Let me try to, because I don't know whether the next, I wasn't sure fast or slow I would go. So I'm not sure if the next set of slides is sort of correctly prepared. I mean, they will follow this naturally. So let me do it on screen sharing stopped. Yes. Okay. On a sort of little whiteboard I have here. Document camera. Yes. Okay. Let me see how this would work. One second. Let me mute stop my video. No. I'll just try to like make it so that I have. I want to make it bigger on my screen. Oh, I know. Speaker view. Okay. Okay. Yes. So it's not in focus, right? Oh, it's still not in focus, is it? It's completely not in focus. Don't know. It usually focuses, but it refuses to focus this time. Hello. Oh, okay, great. It focused. All right. Okay. So, okay. So we know that PRG implies indistinguishable encryption. Okay. So, okay, indistinguishable encryption means that for every M0, M1, the distribution of encryptions of M0 are computationally indistinguishable from encryptions of M1, and a PRG is an deterministic algorithm G that maps, say, lambda inputs to n greater or equal to lambda, actually greater, sorry, it has to expand such that distributions of outputs of the PRG on lambda bit inputs are indistinguishable from a random string that has the same length, of the same length. Okay. So, okay, and what is this implication? How do we know? Because of this construction, that the way to encrypt is run a PRG on a key, an XOR. Sorry. Okay. So what next? Well, how to construct this PRG, right? I mean, how do you? We know if we had a PRG, then we have an encryption. Okay, do we have a PRG? So let's do it in few steps. So how can we construct a secure PRG? Well, partial answer is that if we had a minimal PRG, and by a minimal PRG, I mean i.e. PRG that given n bit seed produces just n+1 bit output. I'm switching variables because lambdas are not very convenient to use. So here I called inputs to a PRG lambda and n the output length, but it's easier to just call everything n. So the input will be n, now the output will be n+1. If we had such minimal PRG, then we can construct a maximal PRG, namely PRG that given n-bit seed produces n plus polynomial of n bit output for any polynomial p. Okay, so what this says is that the minute you have a PRG that takes n bits, and these bits are perfectly random, and this PRG here works on these input bits, and somehow creates n+1 bit output. So the output is just one extra bit here. Then I can somehow convert this into a big PRG that given n bits of input will expand them into arbitrary amount. So this is poly of n for any poly. What that means is that, look, let's say you have you want a stream cipher, right? This is called stream cipher. And well, how long messages do you want to encrypt? Perhaps a kilobyte, perhaps 10 kilobytes, 100 kilobytes, 1 megabyte. What this will show you is that it doesn't matter as long as that amount is polynomial in some underlying security parameter, and basically every efficient computation is in the class of polynomial in those inputs. So we want to say, good people who are running the system, they are working polynomial security parameter effort. The bad guy who is attacking must be working in exponential time in order to attack. So I want to show that this is possible. In practice, we would like this algorithm G prime to have some, so G prime is this whole thing. This G prime to have some added properties. Like, for example, what if I'm an encryptor and there came in messages and I don't really know how big they are. Okay, every time a message comes, yes, I can tell how, but what if it's a stream? Basically, it's not a fixed message, it's a buffer on which bits are accumulated and they're just put. I would like to somehow output the ciphertext as the message comes in. That's the name stream cipher comes precisely from because of this application. So now I have to use this construction, right? So I do have some key. Well, I can locally expand it. So I take my G and I expand it. And I take this expansion and I XOR with the input, right? And that's my output. So if I don't know where this message ends, perhaps there is a further stream. I don't want to fix the ending of this. So in other words, if I expanded the bit stream or the key, and then I need to, somebody tells me, please expand it even more, I can still do so. So the fixed point is not only that I can do it for any fixed point, I can actually not even know what this fixed point is. So I can create these bits, give it to some higher level application, which takes however many bits came and XOR them. And then when this says, okay, but here is more bits, then I just create more bits here and I XOR them with these. And then it says, okay, but there's even more. Okay, I'm good. I can do more. That's the form of the PRG that would be most useful in this case. We'll see, how these examples look. So let's try to. Here is some. Okay, so again, we start given PRG G that takes input, inputs, and outputs, just n+1 construct PRG G prime that takes. How about just this? Okay, so this guy expanded the bit by 1. The new guy want to expand by 2. And I will assume this guy did it for every n, and therefore so if I start him on 100 bits, he's gonna give me 101. If I start him on 101, he will give me 102. So I just do this. I give him n bits, I run him, and then I give him the output, and I run him again. So so this is my G prime. The input comes, I feed the input to G. What do you want to call this variable? Let's say I said x0 is the input x. x1 is whatever came out of here. and this was x2, and I'm going to call this an output y. Okay, so in other words, g prime of x is g of x. So okay, so syntactically this is the case, right? If length of x is n, then this intermediate variable will have n plus 1 bits, and therefore the second variable will have one more, so it's n plus 2. Okay, so we're good. Syntactically, we map n bits to n plus 2. Okay, so far so good. Is G prime secure if G is secure? Okay. So, okay, let's see. Is the distribution of outputs of G prime for x, let's have a notation. Un is a uniform distribution over n-bit strings. So for x that came from un, these are outputs. So these are the outputs of a PRG G prime. And we want to test is G prime secure. So this is the same question as, is this distribution indistinguishable from un plus 2? Okay, this holds if and only if G prime is secure PRG, right? So to say that G prime is a secure PRG is to say exactly this. Okay, what do we know? We know that we assume that G is secure, i.e. that Gx for x in U and prime un is indistinguishable from un plus 1. So let's do the following experiment. This is G prime, right? And let's modify G prime. So here x is taken from un and fed in here, and we're looking at the distribution of outputs. So these guys look like G prime of x for x that came from un. Let's modify this as follows. Let's just have a single instance of G, and instead of having this intermediary variable being an output of G on x, let's cheat and pick x1 as a random n plus 1 bit string. And this would be basically G on x1 for x1 in un plus 1. I claim that these two must be indistinguishable. Why is that? The reason these two are indistinguishable is that if some attacker distinguished these two distributions, then he would distinguish this distribution from this distribution. How would this guy, so if there exists an attacker that distinguishes this from that, then there exists a reduction that would distinguish this from that. Why is that? Oh, sorry. because this reduction would, given a value x1, and the reduction doesn't know, it either comes from this distribution or from this one. But what it does is just it runs G on whatever x1 it gets and gives it to A. If x1 was distributed like these values, then that procedure is going to hit this distribution. If x1 came from this one, then that procedure would hit this distribution. And okay, so here it is again on a fresh piece of paper. So we have two G boxes. We feed it with X an n-bit string. And in here, we call this X1 and call this G prime of X. Or we change this by taking X1 directly from as a random n+1 bit string, running G on it, and well, this is G of X1, right? Let's call this distribution D0 and this distribution D1. If there exists efficient algorithm A that distinguishes D0 from D1, then there exists a reduction B that breaks security of PRG. Let's see why. So B gets a string, let's call it X1, and it gives to the attacker G of X1. The attacker outputs some bit. The reduction just passes this bit along. Probability that B outputs 1 on X1 from D0, sorry, on X1 from that looks like G of that came from a distribution of outputs of G of X for a uniform X is equal to the probability that A outputs 1 on, let's call this Y. Yeah, so this value I call Y. On Y's that came from D0. Because if X1 is like a random sample of this type, from this distribution, so X1 is G of X for a uniform X. And if you give to somebody G of X1, then you give them Y from this distribution. It's exactly the same thing, right? Because the X was sampled at random, like here. G was done on X, it is done here. So that's an X1. But I give to you G of X1. So I'm doing one more G here. In other words, I give you this Y is like in this distribution. If, what's the probability that, that B outputs 1 on X1 that came from uniform n+1 bit strings? And that is the same as the probability that A outputs 1 on y from D1, right? Because x1 was uniform, and I ran G on it and gave it to A. So clearly, I gave him an element sampled from this distribution. And that's it, because if there exists an adversary who can distinguish these two, then clearly whatever, if A distinguishes D0 from D1 with advantage epsilon, then B distinguishes G of x for x in UN from UN plus 1 with advantage the same. So conversely, if G secure PRG, then D0 and D1 are computationally indistinguishable, right? So this must be negligible, or otherwise this distance would be non-negligible. So there will be an attack against a PRG, but you assume that PRG is secure. So this basically shows that indeed these two, that's a conclusion, must be indistinguishable. And now it's a simple step, because if you know that the output of this combined G followed by G is the same as, is indistinguishable from taking a random seed into the last G, just a longer seed, then this by PRG security, this is, explicitly indistinguishable from distribution G2, which is UN plus 2, right? It simply just picks this output at random. Just do nothing here and just pick Y directly from UN plus 2. And by transitivity of indistinguishability, this so that D1 is indistinguishable from UN plus 2, that's follows by security of PRG as well. So this was my first step in the proof. This is my second step. And the third is that by these two, it follows that D0 is indistinguishable from UN plus 2, and therefore G prime secure. It's a secure PRG. Okay, so that's what I that's what I wanted to get. Any questions on this? It is it's sort of clear that you can build on this. So now if you started with a PRG that expands, just given n bits, it creates n plus 1, and you combine them in this kind of sequential order, and now the result is that you expand by 2 bits. You can continue. You can put another G box, etc. And every point you're going to expand 1 more bit. You can do it polynomially many steps and create an expansion that adds polynomially many bits to the output. Nothing will fundamentally change. we'll come back to this, because this is not a particularly efficient way of doing things, although it's a very natural one. What it captures is that it's the following simple intuition. If outputs of PRG are indistinguishable from random, then in particular, you can use them as seeds to a PRG, because that's what you do with X1 here. It's not, so you would like to have a, look at the last step. You would like to have a PRG that outputs n+2 bits, but you don't have n+2 bits. You have you don't have n+1 bits. Normally, you would have to have n+1 bits of a seed. So you expand this one to create a pseudo-random seed, and then you use this output as a seed, as if it was a good seed. Pseudo-randomness has the property that it's good for anything. Any process where you are supposed to use random string, you can equivalently run this process on string that is output of a PRG. And therefore, in particular, you can use it as a seed to another PRG. We'll come back to this, because it's like a, what it is, it's like a very general fact. PRG outputs can replace random strings in any applications, and therefore, in particular, as seeds in other PRG executions. But it doesn't give, this is not a practical string cipher construction. So we'll see how to, we'll play with this next time again, and see how to improve it to a more practical construction. This might not appear as like, well, how else would you compose them? How else would you, if you have a PRG that just expands by 1 bit, how can you compose these things to get better efficiency? It's not obvious, and then when you see the construction, it's also completely obvious. And this is a funny thing, that some things are like, how can you improve on this? And then when you see it, you'll be like, oh, of course you can. Okay, so you can read up or wait till next week, and I'll send out a next set of exercises that will deal with some of these basic notions of negligibility and indistinguishability, etc. But I will try to make it, sort of slow in these exercises, so you don't have all the technical issues at once.
Professor,
I will stop recording.